Hello students, in this video we'll see an example of how to solve a constant coefficient ordinary differential equation with both distinct roots and repeated roots. Let's consider the ODE, y triple prime minus 3y double prime plus 4y equals 0. And we can write this in our differential operator notation as d cubed minus 3d squared plus 4 applied to y is equal to 0. Our goal is to factor the left-hand side, and so oftentimes the possible rational roots are helpful. Our possible rational roots are plus or minus the factors of the constant coefficient over the factors of the lead coefficient. But the lead coefficient is just 1, so the factors of 1 are just 1. So we have a total of 6 possible rational roots, plus or minus 1, plus or minus 2, or plus or minus 4. And we look and we can see that if we plug in 1 to this equation, it won't work. So we try negative 1 first. So we do the synthetic division, put negative 1 in the box, and store the coefficients of the polynomial on the right. 1, negative 3, then there is no d coefficient, so I put a 0 there since the d coefficient is 0. And then a 4. Then we'll have a 1, negative 1 and 1 is negative 1, negative 3 plus negative 1 is negative 4, negative 1 times negative 4 is positive 4, adding 0 and 4 together we get 4, and negative 1 and 4 is negative 4, and we get a 0, and this tells us that we have found a root. And it also gives us a factorization. So d cubed minus 3d squared plus 4 is equal to d plus 1. And then d squared minus 4d plus 4 applied to y equals 0. So this is a perfect square. This is d plus 1, and then this will be d minus 2 quantity squared applied to y is equal to 0. And so we can get 2 of the roots out of these 2 factors for free. We get that y equals c1 e to the negative x from this first term, and we will get c2 e to the 2x from the second term, but we're missing a solution. So to access the second solution for the repeated root, we recall that d minus a squared applied to e to the axy is e to the ax d squared y. So if I had d minus 2 squared y equals 0, what we could do is we could let y equal e to the 2x times u. And if we did so, this would turn into d minus 2 squared applied to e to the 2x u, which our rule would tell us is e to the 2x d squared u, and by assumption this is equal to 0, which tells me that d squared u equals 0, or that u is equal to c1 plus c2x, and therefore y will be c1 e to the 2x plus c2x e to the 2x. Now we can go back to our problem and realize the second solution will be of the form c3x e to the 2x. So this second term over here contributes 2 solutions, and we have 3 linearly independent solutions. We know that e to the negative x, e to the 2x, and x e to the negative 2x are linearly independent. And that tells me that my solution has the form c1 e to the negative x plus c2 e to the 2x plus c3 x e to the 2x. Thank you very much.